Today, we'll start by looking at apparent forces, which are also called fictitious forces. These forces seem to act on objects when we observe them from a moving or accelerating frame of reference, rather than from a stationary one. For example, when you're in a car that suddenly turns, you might feel pushed to one side, even though no physical force is directly acting on you in that direction. Understanding apparent forces is important because they show up in many everyday experiences and are key to analyzing systems that are accelerating or rotating.
John Stapp, a U.S. Air Force pilot, volunteered for an extreme experiment to test human limits under intense acceleration. During a ride reaching 421 miles per hour, he was subjected to tremendous G-forces, much higher than what most people experience. These forces pushed his body in ways that showed just how much stress a human can endure, helping researchers understand the effects of rapid acceleration and deceleration. The images captured different stages of that intense ride. These forces are an example of an apparent or fictitious force. A backward G-force into the seat is not switched on because of acceleration. What is happening is that the back of the seat is pushing John forward. The seat pushes on John, and John pushes on the seat. Newton's third law.
Now let's shift our attention to artificial gravity, which is a way to create the feeling of gravity where it doesn't naturally exist, like in outer space. This concept is important for long-duration space missions because it helps counteract the negative effects of weightlessness on the body. One common idea is to use rotation to generate centrifugal force, which can simulate gravity by pushing objects inside a rotating spacecraft outward, much like the spinning space station shown here. This fictitious force acts on everything inside, providing a sense of weight and helping astronauts maintain their health during extended periods away from Earth. Artificial gravity has not been created. We explain this by considering the force of the spaceship's floor on the astronauts to maintain circular motion and the equal but opposing force on the floor from the astronauts. This picture shows two astronauts in the International Space Station. What keeps the space station orbiting the Earth? Why? Gravity, of course. So why is there an apparent zero gravity in the space station? It's because both the space station and the astronauts are accelerating towards the Earth. Circular motion requires a change in velocity over time, even if speed remains constant. Remember that velocity is a vector, so if direction is changing, velocity is changing. To understand motion, we need a coordinate system that helps us describe where and when something is moving. This system includes an origin point, usually marked as 0 for x, y, and z coordinates, which serves as our starting reference. From there, we use axes to define directions in three-dimensional space. Alongside these spatial coordinates, time is also an important component, allowing us to track changes in position over specific moments. Essentially, any motion we describe is always relative to this chosen reference frame, meaning how we measure movement depends on the coordinate system we use. Inertial frames are defined by having zero acceleration, which means they either remain completely at rest or move at a constant velocity without speeding up or slowing down. This lack of acceleration is important because it creates the environment where the usual rules of physics apply without needing any adjustments. Essentially, if you're in a frame that's not accelerating, the standard physics principles you're familiar with will hold true and give accurate predictions of motion. In this slide, we see that Newton's laws hold true exactly as they are when we consider an inertial frame, meaning a frame of reference that is not accelerating. The key idea is that if all the forces acting on an object balance out, resulting in no net force, the object will continue moving at a constant velocity without speeding up or slowing down. This is shown here with forces like friction, gravity, normal force, and thrust all canceling each other out perfectly. Because of this balance, there's no need to add any complex modifications or extra calculations. The physics remains straightforward and consistent. This principle forms the foundation for understanding motion in many everyday situations. Let's discuss what a non-inertial reference frame means. It's a frame of reference that is accelerating, so its velocity is not constant but changes over time. Because the observer within this frame is accelerating, Newton's laws can't be directly applied to objects observed from here in the usual way. This means that if you're trying to analyze motion inside an accelerating frame, you have to account for the acceleration of the frame itself, which complicates how forces and movements are understood. When we observe motion from a frame that is accelerating, we notice forces that seem to act on objects even though no physical interaction is causing them. These are called apparent or fictitious forces. They only appear in non-inertial frames, which are frames that themselves are accelerating. The key point is that these forces always act in the direction opposite to the frame's acceleration. For example, if the frame accelerates to the right, an apparent force will seem to push objects to the left. This force doesn't come from gravity, contact, or magnetism, but arises purely because of the accelerating frame of reference. Understanding this helps us explain phenomena that we see inside accelerating systems without invoking any new physical forces. When we talk about reference types, it's important to clearly separate inertial from non-inertial frames. Inertial frames are those where there's no acceleration involved, so Newton's laws can be applied directly without any modifications. In these frames, only real interaction forces come into play, like gravity or electromagnetic forces. On the other hand, non-inertial frames are accelerating or rotating, which means you can't rely solely on Newton's laws as they are. To analyze motion here, you have to introduce apparent or fictitious forces, like the centrifugal force, to accurately describe what's happening. These forces don't arise from physical interactions, but from the acceleration of the reference frame itself, requiring us to adjust our calculations accordingly. This distinction is fundamental when analyzing systems from different perspectives, or when dealing with accelerating observers. Now, let's clarify some common misunderstandings. First, it's important to know that inertial frames don't have to be completely still. They can actually move at a constant velocity. Next, the so-called apparent forces aren't real forces, but rather mathematical results due to the frame of reference you're using. Lastly, motion isn't something fixed with just one true description. It changes depending on which reference frame you choose, so multiple perspectives can all be valid. Understanding these points helps clear up confusion and gives a better grasp of the concepts we're discussing. To wrap up, it's important to remember that choosing the right reference frame is the first crucial step in any motion analysis. Once the frame is chosen, we need to clearly identify whether the acceleration is zero or not, since this affects how we apply Newton's laws. Using the wrong frame can lead to mistakes in understanding forces and motion, so making sure we pick the correct frame is key to getting accurate results. This approach ensures that all motion descriptions we make are reliable and precise.